Okay, for number 8, we're looking at bacterial growth that will increase according to the law of exponential growth. And we have 145 bacteria after 2 hours and 415 after 4 hours. Okay, and now according to the law of exponential growth, we can model this initially as y is equal to c times e to the kt, allowing c to represent the initial population. So with the items of information that we have, okay, we have y of 2 is equal to 145, and y of 4 is equal to 415. And if we set up according to the law of exponential growth, that 145 is equal to c times e to the 2k, while 415 is equal to c times e to the 4k. And there are various ways that we can go about solving for c as well as k. But I tell you what, if we go ahead and set up our ratio between the 4-hour and the 2-hour growth, we can utilize 415 over 145 is equal to ce to the 4k over ce to the 2k. And using our proportions and setting it up, okay, we have for the value of k, okay, where we have in the arrangement, we have 415 over 145 is equal to e to the 2k upon simplification. And using the natural logarithm on both sides, we have k is going to be 1/2 the natural logarithm of 415 over 145, which comes out to 0.5258. And we can use, in solving for c, we can use either equation. And we'll go with y of 2. And if we utilize y of 2 is equal to 145, we can say that in this arrangement that 145 is equal to c times e to the 2k, where k is at 0.5258. And in following through, if we divide both ends by what is going to be e to the 1.0516, we had that the initial population c is going to be equal to 145 times e to the negative 1.0516. And taking this to the nearest whole number as requested, okay, we have that the initial population is going to be at 51. And now for an exponential growth model for the bacterial population, letting t represent the number of hours, okay, again we have the initial population is at 51, and k we have at 0.5258. And for what we have in terms of part B, okay, it's going to follow that y is equal to 51 times e, okay, and to the kt we have 0.5258 times t. And for what we have in determining the number of bacteria after 8 hours, okay, what's going to happen in this one, okay, we have that y is equal to, it's going to be equal to 51 times e to the 0.5258 times 8. And for what we have after 8 hours, okay, you're looking at, rounding to the nearest whole number, we'll say give or take about 3,423 bacteria. Now as for what we have in the case of part D, we're looking at how long it is going to take, okay, for the number of bacteria to reach 20,000. So we have in the case of the model here, okay, so we're waiting for y to reach 20,000, okay, which you have equal to 51 times e to the 0.5258t. Okay, we can isolate the e, so we have 20,000 all over 51 is equal to e to the 0.5258t. And as you look at taking the natural logarithm of both sides, what's going to happen here is that we're going to have that t is going to be equal to the natural logarithm 20,000 over 51, and then divided by the decimal of 0.5258. Okay, and so for rounding to the nearest two decimal places, we say that for the amount of time in this one, that it will take about 11.36 hours.